Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today I'm joined by Dr. Geoffrey West. He's Shannan Distinguished Professor at the Santa Fe Institute, and today we're going to talk about the work he's been doing on scaling laws, with a focus on his book, Scale, the Universal Laws of Life, Growth, and Death in organisms, cities, and companies. So, Dr. West, welcome to the show. It's a big pleasure to everyone.
Oh, Ricardo, it's a pleasure to been invited. I appreciate it, and I look forward to our conversation.
Great. So, tell us first, what is scaling? I mean, what exactly are you studying when you study scaling and try to uncover universal scaling laws?
Yes, of course, it's a big question, but and there's a kind of a simple answer, then a very complicated answer. But the simple answer is sort of, in a sense, the obvious one that everybody understands about scale, namely, or at least from a scientific viewpoint, when you ask about scale, you're really asking about how do things change when you increase its size. So it's that simple, and it sounds very simple. But in fact, in asking that question, reveals an enormous amount, not just about the immediate world around us, but about the universe, so to speak. That is, if you just take any object and you ask what happens if I double its size, do things stay the same? And are there significant changes? Are there just quantitative changes, or are there, in fact, qualitative changes, that the system changes its character even? And so asking this question is a lead-in for revealing underlying organization and dynamics of the system that you're looking at. And the thing that you alluded to, sort of the universal character, is that one of the things that has been discovered about the physical world is that it isn't arbitrary when you increase size, and that there's great systematic, regular behavior reveals itself. And by the way, ironically, or remarkably in a way, it goes back to this question, goes back to the very beginnings of modern science with Galileo, because in his wonderful book, The Dialogues Concerning the Two New Sciences, which he wrote, by the way, he was under house confinement by the Pope in the...
Good times back then.
Yeah, he wrote this brilliant book. And one of the parts of that book, one of the dialogues, is exactly this question. This question, what happens if I take an animal and I double its size? What if I take a building and I double its size? And it leads to the question which Galileo already addresses, are there limits? That is, if you keep increasing, what eventually happens? And recognizing that buildings and indeed animals would eventually collapse under their own weight. So there are limits. And so already back then, in asking this innocent question, we have something that today is of great profound interest, limits to growth. Mm-hmm. So he sort of set the template, the paradigm, at the very beginnings of modern science. So it's a fundamental question that permeates all science and technology. I mean, I didn't talk about technology. I mean, you invent something, you invent a computer, can you scale it up? Can you scale it down? And so on. And computers are a great example, where we always had very big computers, and there was a scaling down so that you end up with, a smartphone that is an enormously powerful computer, which 50 years ago would have been bigger than the size of my house almost, to get the kind of power that it has.
So, but I mean, is it that we have been able to find that there are regularities across all scales? So, for example, Is it that if we study things from the smallest scales up to the biggest scales, I don't know, from atoms, subatomic particles or whatever, up to biomolecules, genomes, cells, tissues, organs, people, societies, and so on and so forth, there are regularities in how things are able to scale up or scale down across all of these different levels?
Yeah, so that's the big question. That is, of course, what much of my own work has been focused on. This whole question of going from the microscopic, as you say, well, originally, you know, most of my early career was in high energy physics, particle physics, the very questions of the fundamental particles and the fundamental laws of nature, quarks and gluons and so on. But beginning with that all the way up, as you say, through atoms and molecules to cells and then to organisms and societies and even to the universe, you know, and what is interesting is that within each level, so to speak, we see great regularities of scaling, and which is interesting of itself. I mean, that is within the elementary particles, there's a version of this, but more so, and the thing that got me interested in this bigger question was the scaling among animals, or at least mammals. Just stay with mammals for simplicity. And that is that despite appearances, mammals are actually, to a large degree, scaled versions of one another. I mean, it's kind of weird to think that, you know, a giraffe is a scaled up version of a mouse, or that we're a scaled down version of a whale. But in fact, in terms of almost most physiological things that you can measure about mammals, or so-called life history events, meaning how long you take to mature, how long you live, how many children you have, and so on, we're scaled down versions of each other in a very regular way, and we can elaborate on that in a little bit. So within categories, so to speak, you have this kind of regularity, but then it comes to sort of the Galilean question, not just how does it scale, so we can talk about that, but then what are the limits? How far can you go? So, you know, if you have mammals, there's a certain design, so to speak, that's evolved. How big can you make that without violating something? Or how small could it be before something has to change and it just isn't viable anymore? And when that happens, you know, the whole design changes. And in a way, view that sequence that you articulated from subatomic particles all the way to societies as a response to the changing conditions invoked by the change of scale. So, you know, so for example, one of the things that originally intrigued me was, you know, I'm chuckling because it came about because in the 1950s, when I was a young man, the films, it was the beginning of a lot of science fiction films, and one of the great images that developed was, of course, giant insects, giant ants and spiders, and then, you know, that freaked you out. And I learned somewhere along the line that they just couldn't exist. You can't exist. You can't have an ant much bigger than the kinds of things that we see. They can't function. They can't get enough oxygen and so on. So there are all kinds of those kinds of constraints. There's constraints of being able to obtain the resources, the food that you need to sustain yourself. And there are just biomechanical ones that, you know, it's no accident that the biggest animal, the biggest organism that's ever existed on this planet, including all dinosaurs, exists on the planet today, which is the blue whale, much bigger than the dinosaurs. But it has to live in the ocean because you not have a land animal. You couldn't have a Godzilla, for example, made out of the kind of flesh that we're made out of, the stuff we're made out of, that could stand up. It would collapse under its own weight. And so it's no accident that to get bigger, so there was a change. To get bigger, we went back to the ocean, and so that we relieved ourselves of gravity. So gravity is obviously a dominant force in our lives, but for very big things, it becomes a limiting factor. So you go to the ocean. Mm-hmm. But as you get smaller and smaller, gravity becomes less and less important. You know, there's a famous there were in the mid part of the century was a famous biologist named J.B.S. Haldane, a British biologist, and he wrote a little article about scale actually in I think the 1940s maybe. But one of the examples he gave was if you think of a great big mine shaft or a well going down, and you drop a horse down it, it splat. It's not. It splats. But if you drop a mouse down it, it will get up and walk away. So gravity is not so important when you get small. It becomes bigger and bigger. So that's the kind of thing you have to think about, and the kind of thing that sets limits, and the kinds of things that sets the way in which things scale.
But I mean, when we look across the different levels, I would imagine that the kinds of, let's say, mechanical constraints or other kinds of constraints in the case of biological systems, living beings, it would be something like metabolism, energy, and stuff like that. I mean, but across the different levels, the constraints we find in terms of being able to scale up or scale down would differ, correct?
Yes, absolutely. The actual constraints, the specifics of the constraints changes with levels. So the work that I first got involved with in biology on mammals was the constraints of distributing energy, actually oxygen and resources to all cells, namely your circulatory system and the various networks inside you which distribute primarily energy, and that's your metabolism, so that, essentially all cells in your body can function in a relatively efficient and democratic way, so to speak. And so that work focused on the constraints of the network, the physics and mathematics of the networks that constrain how you can distribute energy through your circulatory system, a beating heart, pumping blood, through taking oxygen and other resources to your cells to keep you alive. And turns out that's extremely complicated. And it turns out that has huge consequences for who we are, for who all animals, and particularly mammals, are. I mean, it determines in the end, to some extent, how long you live, how long you take to grow, and also the thing we just discussed, how big you could get in terms of kind of design. That is, we can't. Turns out it's probably impossible to be much bigger than a blue whale, even if you live in the ocean, and you can't get any smaller than a shrew. A shrew is that little, sits on the palm of you, it's about this big, a scaled down version of us, but it can be just a few centimeters long, and a couple of grams in weight. But we all share the same engineering, so to speak, through these networks. And the work that got me involved in all of this was trying to understand how those networks function, their physics and mathematics, which leads to a bunch of extremely fascinating and remarkable scaling laws that had already been known. It's not that I derived them without knowing. These were known, and they were already discovered in the early 1930s by a man named Max Kleiber, and they're called, the most fundamental is called Kleiber's law, which is, we've already talked about metabolism, which is the scaling law for how metabolic rate, roughly speaking, how much food is needed each day to stay alive, how metabolic rate scales as you go from the smallest animal to the largest. And he not only did a lot of experiments and observations, but he gathered a lot of data and discovered something remarkable, that is that it scales. I'm going to say it mathematically first, and then I'll explain. It scales for those that understand the mathematics, it scales as a simple power law whose exponent is 3/4. Now, what does that mean in English? I wish I could say it in Portuguese, but I have to say it in English. And that is, to put it very simply, so first of all, the way it's represented is that the data that he looked at was mouse to elephants. In fact, he even went as far as the whale, but he wasn't too sure whether to believe the data on the whale, even though it agreed with his other stuff. But it's called the mouse to elephant curve. But you know what you realize is if you try to put on one graph a mouse, the weight of a mouse, which is, I don't know, 20 grams, and an elephant, which is, I don't know, several hundred kilograms, I believe. You can't put it on a graph. I mean, you'd have to have a sheet of paper that's, you know, I don't know, the size of Lisbon. I don't know. But so the way it's plotted is logarithmic. It's called logarithmically. You plot it going up by factors of 10 instead of 1, 2, 3, 4. You go up 1, 10, 100, 1,000, and so on. And if you plot it that way, what Kleiber discovered was that, so you plot on the vertical axis in this logarithmic way the metabolic rate, and on the horizontal axis the weight of the animal. He discovered they lie on a simple straight line, which was kind of mind-blowing of itself, because each animal has evolved by natural selection. And it's evolved, but not only each animal, each part of the animal, each organ, each cell type, each genome comprising of the animal has its own unique history. That's what we believe. It's historically contingent. And it's sort of, you know, we have this kind of naive image that it's all kind of arbitrary and chaotic. All kinds of accidents happen, all kinds of very specific environmental niches that animals adapted to. So given all of that history, if you plotted anything, you would expect, okay, there might be some correlations, but the points would lie sort of scattered all over this sort of random-like history. And what he discovered, quite the contrary. They all line up, bum, 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 in this straight line when plotted this way. Not only that, he discovered that the slope of this line was 3/4, very close to the number 0.75. And again, translating that to the simplest possible form, that means roughly that every time you double the size of an animal, so if you went from 2 to 4 grams, 20 to 40 grams, 200 to 400 kilograms, doesn't matter, anywhere along you double, you increase, you don't double the metabolic rate. So you might think you double the size, you have twice as many cells, you would require twice as much food. No, you only require 3/4 as much. So this is a kind of amazing result. There's a sort of 25% savings with each doubling. Mm-hmm. So we are much more efficient than our dog or cat, but our horse or elephant is more efficient than us. So this is very profound, and it's in a very systematic, predictable, quantitative way. So that was a very exciting result, and it's so weird that even though we paid a lot of attention to it in the 30s and 40s, it got completely eclipsed Second World War into the late 40s, 50s, with the focus on molecular biology because of the discovery of the double helix and DNA, gene. So the whole focus changed from these sort of bigger picture questions to really deconstructing things and reducing them down to this molecular level, which is, of course, been it's important and exciting and has given us great insights. But in all that is lost somehow this extraordinary result. And by the way, what I should have added is that following Kleiber, many people started looking at how various things scale. You know, something as mundane as the length of your aorta, the first tube that comes out of your heart, or heartbeats, or indeed the kinds of things I said earlier, how long you live, but anything you can think of. So there's probably 50 or 75 such things, and they all scale in the same way. They all scale plotted logarithmically as straight lines, and what is amazing, the slopes of those lines, the metabolic rate was 3/4, the slopes of these lines are always some simple multiple of 1/4. Number 4 played a crucial role. And just to complete that picture, work I got involved with my colleagues Jim Brown and Brian Enquist, who are biologists, was to try to understand that and derive it from the idea that it's all to do with the mathematics, physics, and generic properties of the networks that keep us alive. And that was the work that I got involved in, and we derived it from fundamental principles and almost all the other scaling laws, the other 50 scaling laws, we derived from the mathematics. So that was my sort of entry, my transition from doing high energy physics, quarks and gluons and string theory, to the other end of the spectrum, namely biology and sort of big picture systemic view of biology. So I'm sorry, it's a very long answer to your question.
No problem at all. But I would like to ask you a specific question now. So if we have this sort of understanding of how organisms change, for example, as they grow up, as they grow bigger or become smaller, for example, in terms of how their metabolic rates change, and of course in the book you also talk about things you mentioned, longevity and heart beatings and all of that. Does that add anything to the understanding we have about how natural selection works? I mean, by knowing that, can we know or predict how particular organisms might evolve, or at least the constraints we might get on the different paths they might follow, evolutionarily speaking?
Yeah, excellent question. I mean, this is the big question, because just to back off a little bit, Darwin's contribution was, of course, extraordinary, mammoth. I mean, in introducing us to the idea of evolution and evolution by natural selection and so on.
Yeah.
And it's a fantastic thing, but it's qualitative. It's not quantitative. And it is not predictive in the more physical sense of that. That is, it doesn't explain, you can't predict things. And so that the question you're asking, in a certain sense, is, could you predict the kinds of organisms that we see and so on? And I would say, from the work that I've been involved in, the answer is still we can't from that. But we can sort of find a halfway house, and that is, and you sort of put your finger on it, and Darwin had already recognized it, and sadly biologists ignored it for almost the entire history of biology. That is, Darwin pointed out yeah, I mean, he didn't say it. I'm going to paraphrase for sure.
Mm-hmm.
Yes, all this takes place by natural selection, survival of the fittest, competition in the environment, and so on and so forth. But it isn't completely arbitrary, because the laws of physics and chemistry are always at work. So, so in biology, so I'm going to make a tangential remark. So biology evolved ignoring that, and with the discovery of the genome, the whole focus became, or a large part of the focus, came on genes being the origin of sort of everything. There's a gene for everything.
Mm-hmm.
So to give you a trivial example, so you might think, and it probably is, there may well be a gene for jumping. You know, how you jump. A kangaroo or a human being or a flea. You know, we all jump. And maybe there's a gene that we all, I don't know, in common. And maybe you need that. I don't know. Maybe you don't. But for sure, you may need a gene for jumping up. But for sure, you don't need a gene for coming down. I mean, you might think if you didn't know about gravity, you might say, well, I've got a gene for going up, but I better have a gene for returning to Earth. But of course, you don't need that, because gravity, physics brings you down. That takes care of it.
Right.
So one of the things about this work that began to become clear is that for a lot of things, the physics and mathematics of the network take care of things that you think you might need a gene for. So, for example, we took this whole network theory and applied it to growth. So how does that work in this theory? Well, it works just in a very simple way. You eat, you metabolize the food, you send food through the network, and at the cellular level, that metabolic energy gets allocated between repairing damage that might have occurred or replacing cells that have died, and then adding biomass, adding new cells. So you can write down the equations, and it's controlled by the network. And from this, you can derive the equation governing growth. And then from that, you can derive the growth curve for any organism. And the theory works beautifully. And it has universal predictions for growth, and it tells you how big things grow and how quickly they grow and blah, blah. I'm not going to go into that. We'll come back to it maybe in a minute. But it also explains something that is curious about growth, and that is when you are young, you eat and you get bigger. Mm-hmm. And somehow when you begin to get to 15, 16, 17, 18, you keep eating. In fact, you eat more, but you grow less. So it's kind of weird. You grow very quickly at the beginning, and then sort of you stop, and then you stay, roughly speaking, the same size, roughly. And so from the biological viewpoint, the traditional biological viewpoint, there's a gene that controls this. Mm-hmm. That's what they think. But in fact, you don't need a gene, because the equations take care, the network has taken care of it. Now, why does it do that? Now I'm going to explain. So the reason that you stop growing is because the supply, your metabolism, the supply of energy, as you get bigger, is growing less than linearly. The bigger you are, the less energy is being supplied. Okay. On the other hand, you're adding mass, you're adding cells at a linear rate. Just keep adding them linearly.
Right.
So something that's sublinear, that is less than linear in terms of the supply, can't keep up with the demand, which is linear, which is growing quicker. So the supply can't keep up with the demand, and the system stops. And that's how you reach the height that you are, the size that you stop. So you don't need a gene to tell you that. It does it. The whole dynamic and organization of your supply networks are doing it for you. So it's very parsimonious, it's very efficient, and it's extraordinary. And, you know, in a way, so there are many things like that. There are many, many things like that that come out of this theory. So, and you put you pointed to it by saying what it does, it constrains evolution. And in fact, about a year, was it last year, the year before, myself and a couple of my colleague, Chris Kempis at the Institute, and a very distinguished biomechanic named Mimi Cole at University of California, Berkeley, we wrote a paper exactly on this whole question of the physical constraints on evolutionary development. And we put it in a mathematical framework, but it was exactly to make this, to really start to get people to start incorporating that and recognizing that this plays an important role. And we gave several examples. In fact, I don't think we even gave the growth example. We gave other examples that are like that. And so, you know, and it explains, by the way, why it is that, you know, we have, you know, we don't have that many genes relative to many other things, you know, really. I mean, because a lot of things are taken care of by physics, so to speak, the physics and engineering that has evolved by natural selection. And the great thing natural selection has done, the reason for that, in a way, is that the competitive forces have forced us, in a certain sense, or have evolved us to be more and more, I'll use the word efficient, in not having to create more and more genes to do many things, which makes it a much more complex system. So in answer to your question, it doesn't tell you this theory won't tell there's chimpanzees and giraffes and so on, but it will tell you the constraints on them. I mean, you could ask the question, I mean, it could ask, you know, science fiction kinds of questions. What would happen, you know, I mean, in principle, you know, would it help to have two hearts? I mean, after all, a lot of, you know, the biggest problem human beings at least face as they grow old is cardiovascular disease. Most people die of cardiovascular disease.
Yes.
So, you know, you could have imagined, had that been a major force of natural selection, that we would evolve to have two hearts, so that when one of them goes wrong, the other one takes over. Yeah. So it's fun. Actually, this has got nothing to do with anything, but it turns out I live just on the outside of Santa Fe, in an area. It's a beautiful area. I can see the mountain. It's really lovely. But I live in a place that when it was built, it wasn't connected, and it isn't connected to the city water system. And it has its own well, so we have our own water. And the system that's in there has two hearts. It has two pumps in case one fails. Exactly.
Right.
Exactly that. And that's what got me to thinking originally when we first lived here, that I was intrigued that it had a backup. I mean, they alternate, actually. They go sort of back and forth. But if one fails, and in fact, it just so happens on the top of my mind because last week one of them failed. I'm operating on one of them. So there you are. You know, otherwise we would have been, you know, I mean, for a little while in serious shape without water. So you could have imagined. So there's an example of a kind of virtual thought experiment. And you could imagine attacking it that way and ask why, you know, you could do a kind of cost-benefit analysis. Would it have actually been worth it? And the answer almost certainly is no. I mean, the amount of extra biomass and the amount of, you know, sort of maintenance and so on, just to keep the other system as a backup, just isn't worth it because, you know, one heart is probably enough to keep you alive till you're 35 or 40, which is all human beings needed to have lived in order to have enough offspring for the species to persist. So, but you can ask those kinds of questions and those kinds of constraints.
But we've been talking a lot about, for example, growth and development, but can we also use this approach, I mean, the study of scaling to understand aging and death? I mean, why is it that at points that it's possible to predict a particular organism for some reason reaches its limits in terms of how long it can go on for, in terms of its metabolic activity and so on, and just the system just breaks down and dies eventually?
Yeah. So in fact, this was the question that originally got me interested in all of these issues. I've always been sort of fascinated in a kind of morbid way about death and even aging, but mostly death. And and maybe because I come from a family of short-lived males. My father, grandfather, my uncles mostly died relatively young. And so I did not expect to live much beyond 60. I mean, that was typical of my family. Many died in their 50s for different things. I mean, so somehow there was design flaws in our in our family genes. I don't know. So when I was in my 50s, I started to think about that because I thought, well, I may only have 5 to 10 years to live, and it's sort of interesting. Why is that? What's going on here?
Right.
And that what actually got me interested as a physicist was, gee whiz, what actually sets the scale? Forget about me, but what actually sets the scale of human lifespan? Why is it of order 100 years? Why isn't it 1,000 years or 1,000,000 years or whatever? What actually sets the time? And when I started looking in the literature, I discovered not only was this not answered, but the question hadn't been asked, which really surprised me. The biologists, of course, there had been work on this question, but not very much. It was sort of a backwater. But what also surprised me, it was a backwater of biology. So, for example, if you look in big fat biology books that sort of cover the whole spectrum of biology that students use, chapters on reproduction, on evolution, and so on and so forth, on everything, development, and so on. But I had, and the books I had were for my children, actually, from their biology classes. And I looked in those and nothing about death or aging. And I thought, this is pretty amazing because in a certain sense, it's the second most important event in every organism's life. I mean, presumably the first most important is you get born, second most important is you die, and then everything's in between comes sort of. And I thought that's kind of amazing that there's no mention of it, not even in passing. Yeah. So I thought, that's interesting. That'd be an interesting question to think about. And that's what got me into this work, because if you ask the question, why is it that you age and die, you immediately led to the question, what is it that's keeping you alive? Something is going wrong. Something is degrading somehow in the process of living. And the process of living is called metabolism. That's what we've already been talking about. Yep. And so I got interested in metabolism, and that led to all the scaling work and so on that I've already I talked a little bit about. So I got into all that work as a sort of byroad to the question I'm really interested in, is this question of aging and mortality. So here's my answer.
Okay.
So we are a bit like a machine. We're not a machine, of course, but we are like a machine. And in fact, when I first started this work, I asked some engineers I knew who were working for Ford Motor Company, and I asked them the question: how do you know, what is the theory behind knowing how long a car is going to last when you build one? Or to put it more simply, just take the engine. Why does it last of the order of 100,000 miles and not 1,000,000 miles? You know, you engineer it in a certain way, but could you engineer it for 1,000,000 miles? Or why not, 10,000 miles? What is it that determines it? And to my surprise, they looked at me and they said, wow, interesting question. You don't know that? They said, no, we don't think about that. No, we just build engines. So that was a huge, oh my God,
Yeah.
So I realized that there's this whole area that people haven't thought much about, really. So here's my answer. Here's my suggestion. That the whole is, and it goes to this engine thing, that of course, when you have an automobile, you have to maintain it. You have to get oil changed and parts repaired occasionally, blah, blah, blah. But even if you do that, after 10 years or 100,000, 150,000 miles, sometimes after only 50,000 miles, the bloody thing starts falling apart, even though you've been taking it in for maintenance and so on.
Yeah.
And that's what I thought about. I thought, of course, that's us. That's what's happening to us in some way. We're continually, the process of living. So why does the car degrade? Why does the car age and die? Well, because it lives. Because you have to drive. I mean, that's the whole point of a car. You have to drive it, and by driving, it wears things out and so on. Well, that's true of us. You're living and so on. You're continually wearing yourself out in some way. So what does that mean biologically? That means that two things. One is it is very much like the automobile, that there is really physical damage. Just even in the circulatory system I talked about, there's continually damage, especially down at the capillary level of those cells going through. There's continually collisions, of course, and there's friction. There's friction and viscosity in the system, in the flow, and that means damage. So it's always damaging and so on. Now, of course, you also repair. You're continuing to repair and so on. I mentioned that earlier. But nevertheless, you're doing damage. But there's another kind of damage you do, which is chemical damage, because the whole process of metabolism produces products that can damage. They're called oxygen radicals, and they do damage. So there's this kind of damage. But the fundamental point, it's all resulting from metabolism, all resulting from the process of living. Now, we have a theory. We have developed a theory for that metabolism. And this is a calculable theory, and you can calculate how much damage is being done. And here's in English what that says. I said earlier that the theory predicts, and the data, in agreement with the data, that metabolic rate increases with the 3/4 power of mass. I mean, that is, this slope was 3/4, less than 1, which meant that you are more efficient. The bigger animal is more efficient than the smaller one. What does that mean? That means that your cells are working less hard in a systematic, predictable way, following this 1/4, this 25%, than your dogs. Okay, and the elephant is working less hard. Therefore, if your cells are working less hard, it's producing less damage. Therefore, the prediction is you should live longer than your dog, because your poor bloody dog cells are working harder and producing more damage than yours are, and a mouse even more so. So this, you can predict how the difference in lifespan is going to be from the smallest to the biggest, and it agrees with the data. So you can calculate that, and you can. The other thing is that if it's metabolism, that means that one way you can extend life, therefore, is if you could intervene and decrease metabolism. That's hard to do because you've got to stay alive. On the other hand, you can decrease the amount of food you eat, which does decrease, ultimately, your metabolism. And that's called caloric restriction, and experiments have been done on mice and rats. And indeed, they live longer if you eat less. So that's one of the things. If you eat less, you will live longer. And of course, you could go to the extreme and starve yourself, but you wouldn't have a very nice life. I mean, so there's a pattern. The other way you can decrease your metabolism is that you can lower your body temperature, because metabolic rate. So where does metabolism come from? It comes from biochemical reactions in each cell, producing something called ATP, which is the molecule which is currency of energy. And but chemical reaction rates are exponentially sensitive to temperature. That is, if you decrease the temperature, you exponentially decrease the metabolic rate. So this is an even better way of doing it. So if you could lower your temperature from, gee whiz, I don't think in Celsius, but was it 36.5, 30, I forget what it is, you probably live almost twice as long.
Really?
But unfortunately, one of the great things that we did as mammals was to evolve having a body temperature that doesn't change. That gave us huge advantages. But one of the things that it doesn't allow us to do is change it and to increase our lifespan. But everything else on this planet, almost everything else on this planet, except for birds, are exponentially sensitive to temperature. So in principle, if they had the kind of, I don't know, the consciousness to do it, if they lived in places where the temperature is very low, they would live much longer. Well, actually, we've looked at data, we've done that. And in fact, if you look at various things, I mean, there's something called zooplankton, which propagates lakes all over the world. And the same zooplankton living in warm waters versus those live about half the lifespan of those that live in cold waters in a way that's predictable from the theory. So that's another way, and you could, I mean, there are artificial ways of lowering your body temperature, by the way, and they've done experiments on mice to show that. So in answer to your original question, the theory of aging is a product of this theory. Understanding aging and mortality is, and there's lots of other things you can predict from this about aging, which I won't go into. But it's and what it says. And by the way, when I talk about lifespan, I'm really talking about sort of maximum lifespan. How long could you conceivably live? And then you can, and I've already referred to questions about how could you extend that by either caloric restriction or lowering temperature. But there are other ways, of course, because how long you actually live, the sort of 100 years, comes out of a balance between evolutionary forces, which says you have to live to at least 30 or 40 to produce human beings, anyway, to produce offspring, and the amount of energy you're willing to allocate to repair being obviously very important. And so another way that you could extend lifespan is you could intervene by increasing the amount of energy you allocate to repair. And that's what a lot of the work that is being funded by Silicon Valley gurus who want to live forever are funding, is to get people to do this. And I don't know, people may have heard of telomere length. So increasing their mechanisms and or manipulating genes so that you allocate more energy to repair, which may well increase lifespan. I am extremely dubious, not so much about whether they will succeed, but in interfering, because we have evolved with this extraordinary synergy and balance between how we allocate our energy and how all those scaling laws work within us and between us and the biosphere, and you're going to interfere with this. And it may be at the moment is 122.
Yes.
We know. But maybe you could extend it to 130 or 150, but you'd be a couch potato. Maybe you wouldn't be able to move, or you wouldn't, maybe you would become dysfunctional in many ways. So that's a decision about lifestyle that one would have to make. So it brings up a whole bunch of very interesting psychological, social, and even philosophical questions.
Yes, because I was wondering, even if we biologically altered ourselves to allocate more resources to repairing instead of, for example, resources that are used to reproducing, to attract mates and reproduce, there would still be what would be, or what could we predict the biological limit to be in terms of how much we could extend our lifespan?
Yeah, so
because there would still be those constraints we talked about earlier, right?
Yeah, so to put it back in that language, I would say, given the body plan that we have evolved, who we are as mammals, we almost certainly can't live without any intervention beyond about 100 years, beyond, say, 120. Okay, that's it. There might be fluctuations. Someone makes it 125, one person, but for the overwhelming majority, 100, 110 is about it. That's it.
Okay.
Now you ask the very interesting question, which I have pondered whether to actually devote some of my research to, is if you intervene in one of these ways, how does that change this maximum limit? I don't know the answer to that. It's a very interesting question. And the reason I haven't answered is because of what I said before, because I'm very skeptical and cynical about the effects that this will have on other things. We are a system, and we're a complex adaptive system, which means everything is interconnected and interrelated to everything else. So if you fiddle with one piece here, thinking, oh, all I need to change this one piece here, this one piece meaning lifespan, and somehow everything else will take care of it. It turns out that propagates through the system and everything else. And a very good example of that's typical of complex adaptive systems. And we know that. We've had very good examples in our social life with the kind of finance meltdown in 2008, where some little piece of the finance system of mortgages in the United States, which you might think was just self-contained, propagated through the United States and then through the whole globe, and we had this crash. And probably the best of all is the pandemic, where a little teeny, sort of mutation of a virus in China produced within a few months no football in Portugal, no No flour in the United Kingdom. Hertz, rent-a-car, going bankrupt in the United States, all within a few months. All things that you think are completely disconnected.
Yeah.
But in fact, what we saw was that simple, well, not so simple, but that one act of mutation had this huge propagation. So, that's an extreme example, but I am concerned, very concerned, that manipulating with something as fundamental as lifespan, as fundamental as repair mechanisms to the functioning of a human body, in order to extend lifespan, will lead to all kinds of unforeseen and unpredictable, probably, consequences that will be deleterious.
Mm-hmm.
So that has stopped me from really, to be honest, looking for, what would the lifespan be. I'm much more interested in developing the basic theory, mm-hmm. and trying to be a spokesperson for saying, God damn it, this is it, and be careful.
Mm-hmm. Right. So, for the interview, I would like to change topics a little bit. Still talking about scaling, but in the book, for example, and in your work, you've also done some work or concentrated on cities and global urbanization. And I would like to understand, coming from the place you come from, why is it that you think it's also so important for us to understand how cities work, how urbanization works, and what sort of implications do you think it could have? Particularly studying it from the perspective of scaling.
Yes, so thank you for the question. Mm-hmm. Yes, no, I think this is a fundamental and question for the planet, mm-hmm. this very question. And in a way, even though I work on all these other things in biology and ecology, in a way, this is the one that concerns me most, and in some ways, because of its implications, interests me most and is the most challenging. So let me first answer your question about the role of cities.
Okay.
200 years ago, only a few percent of even what we now call the developed world was urbanized. 3 to 5% of, probably Portugal was probably a classic example. I don't know the numbers for Portugal, was probably urbanized. Certainly the United States was about that. Now, I don't remember the numbers for Portugal, but almost all the major countries, the developed countries in the world, are over 80% urbanized. And even ones that are sort of getting towards development are in the 70s and so on. And the planet is now more than 50% urbanized and heading towards, I don't know, whatever it'll be, between at least maybe 80% urbanized in 25. So, and it's been happening at a faster than exponential rate. So, to give a sense of it, the numbers I often quote are, we are urbanizing at a rate in which you're adding the equivalent to a New York metropolitan area, which is of order 50 million people, every few months. We're adding a country, the equivalent to a country the size of Denmark in less than a week, which is extraordinary. I live in a small town, Santa Fe, here in the United States. We're adding this town I live in every 12 hours. Two of us are coming. It's mind-blowing, it's sort of,
yeah.
And it's driven, of course, primarily by, Asia, China, and India, and Africa. China has been extraordinary. It's gone from being Even relatively recently, it was only 30–40% urbanized. It's now over 50% urbanized, and it's building essentially with the equivalent to a couple of hundred, maybe more, 200 or 300 new cities, each in excess of 1 million people in the next 20 years. So that's going to impact all of us. This is what's happening. So the planet is urbanized. And not only is it urbanized, all of that urbanization is taking place on top of fossil fuels. And what does fossil fuel mean? It means that you're burning the planet. I mean, literally, you're burning the surface of the planet. So it's kind of, I don't know. I mean, I don't know how anybody could not believe, because everybody knows that it's burning the surface of the planet. But how could you not believe that isn't going to affect climate? It's not going to affect, the kind of quality of the atmosphere we live in, and so on and so on and so forth, usual things and so on.
Yes.
So this is happening at an extraordinary rate. So cities are becoming understanding. So that's in answer to your question, because cities where people live, cities are where wealth is created, where ideas are created, where innovation happens, where things change. They are the drivers of what society has been and what it's becoming. And it's becoming a matter of some urgency in order to understand, first of all, how did we get here? How did all this happen? And can we understand what's going to be happening in the future? What are the possibilities? And can that help inform policy for how to intervene and mitigate the negative effects of all this? So that's really what this work is about. So, taking the work in biology as a point of departure, the idea was, first of all, do cities scale? Because what we saw in biology was, despite appearances, despite the fact that the mouse scurries around, we live on 2 legs, an elephant has a trunk and a giraffe a long neck, and the whale lives in an ocean, so we look quite different and we live in different environments. Actually, at the sort of 80–90% level, in terms of anything that you can measure, we're scaled versions of one another. I mean, we're the same thing, only rescaled in terms of these nonlinear laws. So the question is, are cities within an urban system sort of like that? So I don't know enough about cities in Portugal. I mean, I know Lisbon or Porto and so on, but let me talk about the United States.
Yes, of course.
So the question is New York a scaled up Los Angeles, which is a scaled up Chicago, which is a scaled up Santa Fe, which is right, even though they're in different geographies, they have different histories, they even have different cultures, they look quite different, they have different feeling to them and so on. But actually, in terms of all the things that you could measure and sort of matter in terms of metrics, are they actually scaled versions of one another in the way that animals were? And so in terms of my work, I formed a sort of a new collaboration of which my major partner in that eventually was, I don't know if you know him, as my friend, Betancourt, was Portuguese from Lisbon. And although he got his doctorate in Imperial College London and had been in the United States quite a long time. But we worked together with a significant group of young people. I mean, he's much younger than me, but he's a young person too, by the way. And he's now at the University of Chicago. We started to put together the data on cities because unlike, by the way, I should have said this, in biology, I did say the Kleiber's law was already known from 70 years ago. Mm-hmm. Much of the scaling work, much of the data through the 80s But in cities, almost nothing had been done, a little bit, almost nothing. So there was a big task to assemble data, and my group did that, and we discovered these extraordinary scaling laws. So let me tell you what they were. So in terms of infrastructure, meaning the length of the roads, the electrical lines, the water lines, the number of gasoline stations, the buildings, and so on, which is sort of biological. They're sort of like the networks in biology and so on. They scaled just like they did in biology. It was just like biology. They scaled. That is, if you plot it again logarithmically, the metric, say the length of all the roads versus the size of the city in Portugal, say, or in the United States. You plotted that, you found, well, there was some scatter, but they lie on a straight line. And the only difference with biology was that instead of a slope of 0.75, the slope was 0.85. But it was sublinear, meaning there was an economy of scale. The bigger you are, systematically and predictably, you need less gas stations per capita, less roads per capita, less electrical lines per capita. All infrastructure scales in a similar way in urban systems across the globe. There was kind of the same universality that we saw in biology was being repeated for the infrastructure of cities in urban systems across the globe. And that was very interesting and very exciting. As I say, the only difference being instead of a 25% saving with each doubling, there's sort of a rough 15% savings. But so in that sense, the bigger the city, the better. In that very simple sense of you need less per capita of everything, roughly speaking. So that was interesting, but that's, the less interesting part of a city, because what is a city for? The whole point of all that infrastructure is so that to bring people together, to interact, to have social networks, to go to the theater, to experience culture, to go to watch sports, to go to universities, to go to lectures, to create ideas, to create commerce, to create entrepreneurship, and create ideas and to increase standards and quality of life. That's the whole point. It is the most extraordinary machine we've invented, the city. That's what it does. It's created all of this by facilitating social interaction. So the most interesting part of a city are to do with socioeconomic metrics, such as the number of patents produced in the city, the number of ideas being produced, the wages, our wages in cities, the number of restaurants, the number of educational institutions, and so on. These kinds of things that are biological and are to do with the very essence of human interaction. But also the bad things about human interaction, disease, the number of AIDS cases, the number of flu cases, and more recent number of COVID cases, the amount of crime, amount of murders, so on, robbery, blah, blah, blah. So all that data had to come together. And what we discovered there was something you do not see ever in biology. Instead of sublinear scaling, which means the bigger you are, the less you need per capita, as per se biology, what we discovered was the bigger you are of any socioeconomic activity, the more you get per capita. So the bigger you are, the more ideas are produced per capita, the wages per capita, the more fancy restaurants there are per capita, the more education institutions per capita. So representing what cities are, the bigger they are, the more activity there is, the more opportunities, the more excitement, the more kind of sexy, exciting life there is in cities and so on. All of that being reflected in this data, and all of it, irrespective of metric, whether it was good, like patents and wages, or bad and ugly, like disease and crime, all increasing in the same way with a slope of about 1.15, meaning that the bigger the city, if you double the size of a city, you don't get just twice as much of everything, you get twice as much plus 15%. you sort of get this 15% more of wages, 15% more ideas, and so on. So in that sense, in this purely sort of, scientific framework, bigger cities are better because you need less infrastructure, you get an economy of scale, and you get more of the good, weight, ideas, and so on. But you also get, here's the kicker, more of the bad, more crime, more disease, and so on per capita. So that was great. That meant that cities had this wonderful systematic scaling. And you ask yourself, where in the hell did they all come from? Where do these scaling laws come from? Well, you can imagine the infrastructure ones being like biology. There's a certain optimization has taken place from kind of some analog of natural selection, of competition, and so on. And so, for example, that economy of scale might have come about because, in fact, we believe it has, because the form of cities has evolved in terms of its infrastructure so that, you can get from any point A to any point B in sort of the quickest way possible or the shortest way possible. Of course, you have to go like this and this, but when you go to, go to the theater or go to your office or go to watch a football game, you don't take some arbitrary route. You try to do it in, the quickest or shortest way, maybe the most economic way, I don't know. But there's that's the whole point. Some optimization is going on. So that's for the infrastructure. Now, what about the more interesting part of a city, the socioeconomic? Well, that may be because that comes about to do with social networks. That's a reflection of the social networks because the whole point of a city is to bring people together, as I said, so that, and you're doing it every day, A talks to B, B talks to C, C talks back to A, and we build on each other. We're continually creating ideas. Now, almost all of those ideas are pointless and useless, probably even to the people that are producing them, but certainly to everybody else. They're not, but what is amazing is that dynamic, that very dynamic, that positive feedback that we build on things with each other over very short periods of time occasionally produces the theory of relativity or quantum mechanics or a Google or a Microsoft or a Toyota or whatever. That's what it does. That's what is happening. And so that positive feedback, so the optimization, the maximization, the city is trying to maximize social interaction. And at the same time, maybe people are always wanting more. There's a certain greed. I mean, I don't necessarily have to be negative, but people want more, obviously, because the system doesn't work. I mean, latest iPhone or the latest computer or whatever. People want more. You want a new car, even though the old one is still running, and so on. So that's another kind of maximization or optimization of work. So the idea is that these scaling laws come because all those dynamics are operating in the same way in every city. And so, and that's what this work led to, was trying to understand that and trying to understand what the, so to speak, the science or the physics of cities and social interaction is. And that led to something that was quite interesting because that now relates to the second part of what you introduced, for want of a better phrase, the long-term sustainability of the planet. What implications does that have as we go forward? And that relates back to what I talked about earlier about the growth in biology, and that the growth in biology was that you had this what we call sigmoidal. I didn't use that phrase then, that you grow quickly and then you stop, And the reason you stop, I suggested, was because the supply is sublinear. You get S per cell, the bigger you are, but the demand is linear, and eventually you just can't keep up, and you stop growing.
Right.
And in biology, that led to the long-term sustainability of the biosphere. Everything remained sort of, over long periods, things remain sort of metastable. So biology has been around 2 or 3 billion years. Now, in socioeconomic systems, that's considered bad. I mean, after the development of capitalism and free markets and entrepreneurship, there has become this idea that we always have to be growing. Can't stop growing. A company that stops growing, or an economy that stops growing, or even a city that stops growing, somehow that's bad. And how does that come out in this theory? Well, the theory is very beautiful in that way, because it turns out this superlinear scaling, getting more per capita you are, leads to, which led to superlinear scaling, leads, instead of to bounded growth, leads to open-ended growth. So it's very nice. The theory explains why it is, why cities have open-ended growth and so on. But it had built into it something very bad, the theory, that not bad in terms of its, the theory was bad, but its predictions were disturbing, and that is it led to something that's technically called a finite time singularity, which says that if you continue with that open-ended growth, you're going to become infinite in a finite time, which is crazy. You can't have an infinite GDP or an infinite number of AIDS cases or an infinite number of restaurants. It tells you what happens, you collapse. And so the point is, what it tells you is the only way to avoid that is you have to reinvent yourself. You have to, it leads to something called a singularity, and to avoid that singularity, you have to start over again. So for example, you go from the Stone Age to the Iron Age, the Iron Age to the Bronze Age. That's why we call them that. It sets a paradigm in that period. And now we had, the Coal Age and the oil, and now more recently the computer age, and now the internet age, and they're different. And they reset the clock. You start over again, and you could avoid the singularity. And that's great, and that's what we've done. So it says that in order to continue open-ended growth, you have to have major innovations that lead to a paradigm shift. You have to sort of reinvent yourself. And that's great, and that's what we've done, and the data supports that. But the theory says you have to do it faster and faster. And in fact, theory says, unlike biology, in which the bigger you are, the slower everything is, in these systems, the bigger you are, the faster the pace of life. The pace of life is faster in New York than it is in Santa Fe. And as part of that, these innovations have to come faster and faster. So instead of taking 100 years to develop something 1,000 years ago, now you have to do it in 10 to 15 years, and soon you have to do it in 5 to 10 years, and soon in 1 to 5. And the question is any of that sustainable? So that's the sort of the big framework for trying to understand what the future of the planet is going to look like, and to try to suggest what interventions one might have to make to avoid collapse.
Okay, so one last question then.
I do apologize.
No, not at all. But one last question then. Can we answer that question? I mean, if it's sustainable or not?
Well, this is a tough one. I must say, so here's the speculation. We're sort of, so I've done a lot of the science. A lot of science has been developed. And by science, I mean it's quantitative, it's mathematizable, computable, it's predictive. it's compared to data, and the theory is iterated and so on. So it's on pretty good ground. But now we sort of leave that and we move into something that's more speculative, inevitably. So what I said earlier, what I said a moment ago, is that in order to remain sustainable, you have to keep reinventing yourself, but you have to do it faster and faster. And the question is, you know, there's some limit to that, clearly. I mean, for one thing, we have the same brain and the same biology that we did when we started all this 10,000 years ago. But even before that, 100,000 years ago, we have the same, we're the same human beings, basically, you know.
Yeah.
But look at what we have to do. We have to do what you and I are doing. We have to learn how to use the latest cell phone. We have to learn the latest gadget. You know, and it comes faster and faster. And remarkable that we've been able to adapt to our own inventions. I mean, I think we are beginning to approach a threshold, a point at which people are finding it harder and harder to do that. And one of the consequences of that is we're producing great anxiety, kind of social anxiety, about things are sort of getting out of hand. We can't keep up with things. Because it is very curious that the standard and quality of life by sort of standard metrics has continuously increased, actually. Certainly if I compare even to 20 years ago, and certainly in my lifetime, if I look back to when I was a boy or even your age, I mean, what you normally think of as the metrics of standard quality is much increased. But people are more and more dissatisfied and angry. Happier, more relaxed. They're not. They're more anxious. They're more concerned. And they are turning towards authoritarian rule, I believe, because of that. That is, looking for simple answers to a world that is becoming increasingly faster and more complex. And they're looking towards people that give them extremely simple answers, including you don't have to tell the truth. You don't have to believe in science. You can just make up things as you go along, and we can do whatever we like, and so on and so forth. It's kind of crazy. We're living in a totally crazy world in some ways. And I believe, I speculate, that a lot of that is to do to this increasing pace of life that is, and you ask yourself, and the kinds of things I talked about a moment ago, and you ask yourself in terms of now returning to the science, where did all that come from? That all came from the dynamics of social networks. This positive feedback and so on. So the question is, what does that mean more generally? That means it's to do with the way we interact with each other and therefore our culture. And therefore, this whole question of having to need to make these big paradigm shifts, these major innovations, has to change in a way. And here's a major point. When we think of a paradigm shift, or especially of a major innovation, what that has come to mean in the last 20 or so years is a major technological innovation. When we say innovation, you immediately think of something technological. You know, as I say, and in fact, the latest being, you know, electric cars, for example, or AI, or artificial intelligence. It's immediately what you think of. You don't think of a cultural or social innovation. And so one of the things that I speculate we need is not a major technological innovation, which will postpone again things and may major changes to this whole question, or major mitigating tension, sort of advances in terms of this. I think we need a kind of much more of a social and cultural innovation. I don't know what that is, and maybe it will be combined with a technological innovation. I don't think electric cars would do that, but AI might. artificial, I mean, that's a whole new area. Maybe that will create a cultural innovation where, and now I really speculate, where instead of this change that we've just been going through, the change towards authoritarian rule, towards, anti-science, towards, I only care about me, not about you. I mean, why should I care about what's happening in the rest of the world, what's happening to the poor, and so on? This kind of thing. I don't like that ethnic group. I don't like that, and so on. All of this, which is surfacing, the sort of dark side of the human psyche. Instead of that, we sort of looking for, I don't know, I mean, here I'm going to get into trouble. We're looking for sort of another Jesus Christ or a Muhammad or a Martin Luther King or, you need, in other words, what I mean by that is someone with the charisma of a Donald Trump or a Sergio Berlusconi, someone with that kind of charisma and attraction that preaches the opposite to what they've been doing and brings us together, makes us feel part of the collective, makes us, that, for want of a better word, that we, love thy neighbor as thyself. I'm not a religious person, by the way, but, that the bringing together and that we feel the sense of community, and I think that may have to be a prerequisite for how we eventually deal with these problems. So that's my sort of worst case scenario of what we need, and that doesn't look very good at the moment. So I'm somewhat pessimistic, I have to say, because I don't see the kind of charismatic leadership emerging. At various times in recent history, especially in Europe, we've seen people with that charisma, everything from, a Winston Churchill or Franklin Roosevelt in the United States, or Adolf Hitler doing the negative in Germany. Those people, but we need people that can do it in this kind of much more positive these positive attributes, the bright side of the human psyche rather than the dark side. So that's, I don't know, I mean, I'm sort of, this is outside of science completely, but it's otherwise it's hard for me to see how we're going to get out of this, because we seem to be just heading towards the edge of a cliff and we're not paying attention. I mean, the little that's happened, we have the green movement and we have all, which is wonderful, the environmental issue, it's fantastic, but it's too little too late kind of thing. And it's not, and indeed it's wonderful, it's grassroots, we need that. But, I think one of the things we've learned is that without, for major things like this, somehow an individual plays a crucial role that somehow condenses what's in the sort of collective psyche, so to speak, to really bring us together. So anyway, that's a funny note to end on. I mean, it's not science.
No, but it's still interesting speculation. So
yes,
food for thought, let's say.
Food for thought, exactly.
Okay, so the book is again Scale, the Universal Laws of Life, Growth and Death in Organisms, Cities and Companies. I'm leaving a link to it in the description box of the interview. And Dr. West, apart from the book, would you like to mention any places on the internet where people can find your work?
No, I think just the Santa Fe Institute, which is where I work, which was just a couple of comments on that. It was founded in the, probably late 80s by a bunch of extremely distinguished people. I mean, several Nobel Prize winners with truly major Nobel Prizes, I would say, who were beginning to feel that many of the big questions, one of which was, believe it or not, associated with the long-term future of the planet, were not being handled, not being dealt with, and that all of scholarship and academia was focusing on very specific individual problems And it wasn't even that we were getting more and more disciplinary, the disciplines weren't talking to one another. And they felt there needed to be a place on the planet where people come together without those boundaries. So the anthropologist talking to the economist, talking to the mathematician and the physicist and the economist to start to address some of these big questions. And I had the honor of being the president there for a few years, and that's where I work. And if people go to the website of the Santa Fe Institute, they will find many things that are related to this, not my work, but other people's work. And I think that's a good point of departure for finding all kinds of things. I mean, it's not only done, obviously not just the Santa Fe Institute, it's done around the globe. But it's a good place because it acts as a hub for people around the globe. It is primarily a visiting institution, and it has a small faculty, a small resident faculty, of which I am one, of maybe about 15 people, but it has a faculty of about 20 people from around the globe. And and it is the founder of the science of complex systems, complex adaptive systems, and these kinds of questions. So it's a very good place just as a resource to begin for those. And also, by the way, it has a very good educational component where you can learn about this with, and take very really attractive courses to learn about some of these questions. So it's a good place to begin.
Great. So I'm also leaving a link to it in the description box of the interview. And Dr. West, thank you so much for your time. You've been very generous, and as I said, I'll be leaving a link to your book in the description box of this interview. So it's been a pleasure to talk to you.
Yes, thank you. Likewise, I really enjoyed the conversation, even though I talked too much. And your questions were excellent and really got to the heart of the matter of several of these big issues. I appreciate that.
Okay, so let me